Hi everyone, welcome to the part 3 of the video. I am Christine Sumage and I am with Andy Ritter. So Andy, can you tell us more of what we are going to do now?
So let's shortly recapture what we have done so far. So at the very beginning of this video series, we started out with having a closer look at field programmable PWM controllers, their architecture and their intended use cases. Then we have set up a very simple voltage mode controller for a synchronous buck converter. In the second section of this video series, we then changed from voltage mode control to peak current mode control by reconfiguring some of the most fundamental blocks of our PWM controllers. So now in section 3, we will add custom features. So the major goal of this session is to change our current feedback signal from a traditional current sense transformer feedback to a custom designed DCR sensing circuit. The way we do this is that we now dive a little bit deeper into the configuration capabilities of the parts, utilizing the switch mode power supply libraries to make fundamental changes to our feedback signal by adding custom components required to make this DCR sensing technique work. So DCR sensing in general is a technique where you are using a simple RC network which is connected in parallel to our main inductor. So the current sensing we are using in this circuit and also in the previous example gives us a direct representation of the currents of the inductor current in a very nice large feedback so that it's relatively easy to measure, and implementing something like a peak current mode control with internal comparators is fairly easy. So now we are removing this current sensing method and we are adding our parallel RC network. So the components of this RC network need to be tailored to the inductance. We will not cover these details about DCR sensing in this video, but there are a couple of nice application notes available, and you will find them in the links below this video. So what interests us now is how can we get that signal which is generated in this RC network into our feedback loop so that we can utilize it to trip a comparator and finally use it as feedback signal within a peak current mode modulator. So when you look at this RC network and imagine when the high side switch closes, we are applying a voltage across the inductor. The volt seconds will be constant, which means that this capacitor will slowly charge up over time. The charging time or the slope of that charging ramp will be determined by the capacity and the resistor. So this network now has to be adjusted to the DCR so the DC on resistance or DC resistance of our inductor, so that we always get enough charge into our RC network, basically replicating an emulated signal which looks like the inductor current and which always matches the slew rate of the voltage with the slew rate of the real inductor current. So this emulated feedback signal is now at the high side, so that means it's at the high line. At the moment it is a little bit challenging to interface this capacitor voltage from our controller side. So what we need is a differential amplifier. We are now wiring this capacitor onto two of our device pins, and internally we are loading a op-amp, or we are connecting an op-amp to these two pins. The amplification factor is set by external resistors. So this helps us to scale the feedback signals as intended to get to a certain current gain, which is needed to provide a proper feedback for our inner peak current mode modulator. So when you're looking into the user guide of our ZIP hybrid power starter kit, then you will find a section about DCR sensing. Unfortunately, the current gain of DCR sensing circuits is fairly low, so it doesn't match the current gain of the other current options we have designed into the board. So to use DCR sensing, you need to modify the board. So there are a couple of particular components, especially the compensation network, which is to be adjusted to operate with a significantly smaller current gain. The board we have here at the moment is already prepared for this. If you would like to rework your board, you would have to exchange two of these resistors here in the peak current mode section, which is basically defining the total gain level, so that the gain of our feedback, outer feedback loop, outer voltage loop, matches the current gain we are deriving through our DCR sensing technique or network here. The thing that changes now is, or the things we need to change. So first we need to install a differential amplifier at two input pins of the device. These are the two input pins which are wired to our DCR sensing network, where the resistor of our RC network is located close to the inductor to cut off and limit the noise. The capacitor has been moved very close to the device because the voltage we will see on this capacitor is very small and sensitive. So we moved it as close as possible to the device to prevent that our feedback signal is picking up additional noise and then eventually drowning our feedback signal into the noise floor. So an additional option to make this signal better visible and accessible is to add a certain offset voltage to our feedback signal. This helps us to lift this fairly small AC signal out of the noise floor, and also prevents or allows our controller to operate even if that signal goes negative. So this offset voltage can be added by a simple resistor on the board, or you can also change this resistor, move it over, and use an internal DAC to apply a programmable offset voltage. So what we will do in this example is now first install this operational amplifier, make sure that the DCR sensing is working, and then we are also adding a DAC which allows us to program the offset of our feedback signal to tune or fine-tune our feedback signal.
Okay.
So Tin, could you show us how this is done in the switch and power supply libraries?
Yeah, I can show you. In level 1, we use a high-level topology block to configure a complete PWM controller by setting small numbers of basic parameters. In second video, we went one step further down to get access to the fundamental building blocks when we swapped the voltage mode to peak current mode. And now, we are going to the lowest level, which gives us access to every single component of our peripheral set. As Andy has shown a while ago, we need to add an operational amplifier to sense the DCR voltage. To do that, in the previous configuration we have on the video 2, we will just going to add the op amp. To the project resources, look at the pins and change the current sense signal to where the op amp output is. Now that this has been changed, the PIC16F1779 established the connection of the DCR sensing in the board. Another option to do the DCR sensing is to add an offset voltage. We can do that by adding the DAC peripheral set the desired value, sample 500 millivolt, which is a 0.5. Then map where the where the DAC out is. In this configuration, we can now operate the CIP hybrid starter kit in using the DCR sensing. Now generate it and program the device. Okay. Andy, can you show us the performance of this CIP hybrid starter kit operating in DCR sensing?
Sure. So to make the DCR sensing configuration visible, we added a scope to our setup. We are using two probes, one for the PWM signal, so this is probe number 1, and here you find an additional test point for DCR sensing output. So now we have two signals on our USB oscilloscope, and when we look at the results, then you see the red line of the PWM below. So this is the on time of our high side switch. The blue line above is now our DCR signal. And as you can see, if you look into the scale, it's a little bit hard to read, but the total signal size is roughly 100 millivolts peak to peak. So it's a very small, very sensitive signal. The internal amplifier is giving us now a signal which is, let's say, large enough that we can work with it without adding too much phase delay and amplification damping, amplitude damping. So this signal is, as I said, a very sensitive signal, which unfortunately makes it also not very accurate. To improve the accuracy of the signal, we then added the DAC to lift it out of the noise floor to make it better visible. So as Tin has added the DAC, we can now program the offset of that signal. So when we look at the signal a little bit closer, how it performs, then I will turn on and off the load, so stepping the load from 0 to 50% and back. So you can see that the difference in the signal is still very small. So we have roughly 50 millivolt per amp difference in the DC level of that signal, which would give us the average current, and 100 millivolt peak to peak total AC component. So to make this work, you might need a little bit more information. So DCR sensing is well covered in app notes, so that you learn how to dimension the RC network and match it to the inductor and its DC resistance. And the flexibility of the starter kit should then give you a few options to learn how to best implement that to achieve a certain stable control loop. So to see now how this really performs, we will run yet another frequency domain measurement. So when we switch over into our network analyzer, then we will see that the signal looks, or the result of the frequency response looks very much like in our previous measurement. However, the bandwidth now dropped from roughly 35 to around about 25 kilohertz at approximately the same phase at around 50 degrees of phase margin. The gain margin here is in a range of close to minus 16 dB. So as you can see, even if the signal is small and quite sensitive, with the support of the internal peripherals and the additional features we added, we could make it work so that it is a stable, reliable peak current mode control at minimum cost with using a lossless sensing technique. So this concludes the video number 3 and our video series on field programmable PWM controllers and the configuration with using the SMPS libraries. So for more information, we have added a lot of information below the video in the description area, where you can find detailed information about the starter kit, the switch on power supply libraries, as well as further links to app notes and tech briefs, which will give you more insight and more knowledge about what you can really do with these products.
So thank you everyone for watching the 3 parts of this video. I am Christine Sumage and I am with Andrew Ritter. Thanks again for watching.